just heard an ITC colloquium, an excellent colloquium by Ruth Angus about the age of stars, not in Hollywood, but in the sky, how to estimate their ages. And we'll hear from her in a little while some more. We'll start with our own Ashley Villar, who will be speaking about a semi-supervised approach to supernova classification and anomaly detection. Then we'll continue with Grant Kennedy from Warwick visiting us. Is he here? Oh, hi. And he will talk about the circumbinary protoplanetary disk in a polar configuration. And then we'll hear again from Ruth, who is visiting us from New York City. And she will tell us about the stellar rotation with TESS. And finally, we'll hear from a visitor all the way from France. His name is Alain Dupas, and he is an international expert in space technologies, industries, and policies, as well as, both in the defense and information technology areas. And he will talk about space macroengineering and the future of humankind. So that's a very important topic for the young people in the audience. And we look forward to that. And Alain will also speak tomorrow, Friday at 11:15 in the ITC Lounge, some more about policy-related issues. So we'll start with, sorry?
There's a different talk happening there.
Oh, so I'm not sure because I was told, really, so we have to look into that.
We do have another speaker scheduled for tomorrow, and so I guess she will share time with
Oh, okay.
Perhaps it can go a little bit later.
I see. So there is a conflict that was not recognized. Thank you for letting me know. Yeah.
Sarah Melholland.
Well, okay, we'll figure it out. But we'll start with Ashley. Go ahead.
Great, thanks so much. Thanks for coming, everyone. So we're going to dip our toes a little bit into machine learning in the next 10 minutes, and specifically trying to classify supernovae in an upcoming age of big data and time domain astronomy. And I really want to thank my collaborators in this work, so Michelle and Ido, Ido's group, and the larger Pan-STARRS collaboration. So Noel Cho, luckily, gave a wonderful talk at this series a few weeks ago, so you hopefully have been primed to understand what an important problem this is. But just to reiterate, in 2023, a new wide-field optical survey is going to come online called the Large Synoptic Survey Telescope, or LSST for short. And LSST is going to drastically revolutionize our field, the field of time-domain astrophysics and other fields. So here, to give you an idea of exactly the scale of this new mission, I'm showing you a plot I made just using publicly available discoveries of supernovae over the last few decades on a logarithmic Y scale. So as I wanted to point out two things about this plot. First, we can see that the number of discoveries, well, three things. First, we can see that the number of discoveries of supernovae has exponentially grown in the last few decades, starting at just 10 supernovae per year in 1980, and now around 10,000 supernova discoveries every year. Second, a reason for this drastic increase is thanks to new missions which are untargeted and wide-field photometric surveys. Those are really driving the new discovery rates. Third, in 2023, this exponential rate is actually going to increase even more dramatically. When LSST comes online, it is primed to discover over 1 million supernovae every single year. This is a 2 order of magnitude jump from where we are today, and a jump that we've never seen before. So this is really going to push us into an age of big data. And with this new age, I like to think about the upcoming problems in terms of a needle and a haystack. So what do I mean? The haystack of objects will be the millions of transients that we discover every year through LSST, so we'll have nice broadband light curves. And of these, given our current spectroscopic resources, which are not expected to increase, we'll have maybe thousands of classified objects every year. And from these, we can really only trigger and get a graduate student to write a paper on maybe 100 or so events per year. So these 100 or so events to me are the needles, and they represent a 1 in 10,000 outlier. Think about that for a second. That's like if the entire time domain astronomy community decided to focus on just one transient this year. What would that even mean from a philosophical point of view? That's what we're going to be handling. But equally important to these needles is the haystack that still has millions of transients with no follow-up whatsoever. We shouldn't throw away all of this important science just because we didn't get a spectrum. So what can we actually do? Today I'm going to focus on step 1, which is classifying these events in order to understand the underlying physics. In particular, the traditional way of classification is to get a spectrum of the object and then use that to do an underlying classification. In the future, we'll have to do photometric classification, and that's what I'll talk about in particular. To discuss this, I have to quickly introduce a different survey that Harvard was a key member in, the Pan-STARRS Medium Deep Survey, which ran from 2010 to 2014, right before my time as a grad student. And all you really need to know is that in terms of area coverage and temporal coverage, is about a milli-LSST. And it really has very similar data properties to the real LST that's coming online. In this survey, our group and others have discovered around 5,000 supernova-like transients that have been identified, though not published. About 3,000 of these had host redshift measurements after the fact, and that's through a dedicated effort of the Harvard team using largely MMT hectospec. And about 500, we actually got real-time classification, so the spectrum to tell us what the underlying physics is. So we're going to use this as our training set for machine learning algorithms that we want to apply to LSST. How do we actually do this? Well, I'm going to tell you very briefly about a new semi-supervised machine learning method. Semi-supervised just means that I'm able to use both the supernova where we did get a spectrum, so I know what type it is, and the ones where we didn't get a spectrum, and I can still take out interesting information from those light curves using this method. I very quickly just want to point out that once this is published, the Pan-STARRS Medium Deep Survey photometrically classified data set that is, it will be the largest samples of basically all subtypes of supernovae, including 1As, which has been published as part of the Pantheon cosmological sample, stripped envelope supernovae, interacting supernovae, etc. So how does this method work? I'm training something called a recurrent neural network-based autoencoder, which is a mouthful. But let me explain the two important features I want you to take away from it. The first is the fact that I'm training an unsupervised autoencoder, which looks something like this schematically. What's cool about an autoencoder is that it tries to learn, given an inputted light curve, it tries to give me back that same light curve. That seems really silly. Why would I want a machine learning algorithm to do this? Well, in the process of giving me back the light curve I put in, I force it to squeeze down all of that information into just 10 numbers. In a way, I'm kind of compressing the image into just a very small vector. And what's cool about this is that we can use these numbers as interesting, non-linear, and non-physical features that I may not identify as a scientist. The second cool feature of this architecture that I've chosen is that the neurons, which are represented as these boxes, and we're going to zoom into one, are very special types called a recurrent neuron. You can kind of think of this as a recursive function, which means that every time I put in a new input value, it saves the state that the function was previously at. So in other words, every time I feed in a new data point, as more data comes in from LSST in these light curves, I can update the encoded compressed version of those light curves so that the encoding becomes better and better. Let's see this in action to clarify what's happening. So here I'm actually showing you Pan-STARRS Medium Deep Survey data in the data points with errors. This is a spectroscopically classified type 1A, and these lines represent the expected light curve that comes out of my machine learning algorithm. And this is actually kind of silly, but really is a representation of that encoded version. And the colors really do represent the encoded values. So what I want to point out about this, though, is that the unique architecture I've chosen is actually able to extrapolate what it thinks the light curve is going to do. So let's watch that as more data points come in. So the first data point, it's not quite sure. It thinks maybe it's dim and short-lived. But very quickly, this algorithm picks up on the fact that this thing is probably around the peak brightness of a type 1A. And it's starting to understand the key features of a 1A, if you're familiar with these light curves, expecting kind of a secondary bump or plateau in the redder band, Z band, and a sharp decline in G. And we'll see that happening as we just get a few more data points. So this is the full light curve, and we can see that with just this 10 number encoding, I get all 4 light curve bands pretty well. So that's exciting. It means that, at the very least, this representation is learning the underlying shape, but we don't exactly know if it's learning features that can be used for classification. So I will show you quickly how our classification results are actually panning out for us. First, I want to say that I applied this model to the full Pan-STARRS dataset I mentioned earlier. This is a preliminary breakdown of the different subtypes we can expect. And again, I just want to highlight the blue sector for a second. These are stripped, or 1bc supernovae. And we predict that there's about 100 sitting in our Pan-STARRS dataset. This is drastically larger, approaching an order of magnitude larger than any existing homogeneous sample of these type of supernovae. So this will really be a really important training ground, both for machine learning algorithms and for new exciting population science. Okay, so how are we actually doing? So I'm showing you here what's called a confusion matrix, and that's just a snapshot representation of how our predicted label from the machine learning algorithm compares to the spectroscopic label that we got. And so this is just for the subset of objects where we did get a spectrum and I know what the underlying label should be. The way you read these is that you want the diagonal to be a dark blue color. And it basically is, so that's good. You can see that we perform differently for different subtypes. Some subtypes, like 1A, we're performing as well as classifiers that are specifically trained to look for type 1A supernovae for cosmology. For other subtypes where we have a small sample, it's not doing quite as well, likely just because we don't have enough to represent the full characteristics of that population yet. Finally, I just quickly want to point to future work that I'm excited about. So because this special architecture can make continuous active predictions about what it thinks a supernova should be doing, or any transient should be doing, it's really learning the norm of the population. And one interesting application is that you can search for something that heavily deviates from the norm, like I'm showing you in these fake star cartoon data points. And this can find needles in the haystack, that 1 in 10,000 event. And I didn't have to implement any physics to get this result. So this is exciting because it means that it's one of the few ways we can actually search for brand new physics in LSST. Great. I want to end with my conclusion slide, so thank you so much for listening. Yeah.
And they put and get substantial redshifts, and there you have another problem, which is the stretching of the time axis because of redshift.
Yeah.
Does your algorithm allow?
Yeah, so that's a really good question. So my algorithm currently assumes that we do have a redshift, and this is slightly driven by the fact that we should be able to get photoz's down to something like 23rd to 23rd and a half magnitude with LSST. That's the promise of them. But it is true that if you don't have that redshift, it's very hard to untangle the observational stretching versus whether it's just a lot of mass and therefore a high diffusion timescale. That is an issue. For some classes, like 1As, it doesn't matter so much. We can still identify them quite well without the redshift. For other classes, it's unexplored. Yeah.
So I guess normally if an observer or a theorist is trying to characterize a light curve, they'll give you a peak magnitude and the peak time and so, two numbers like that.
Yeah.
But you didn't. You encode this in like 10 numbers that are not chosen in any particular way. The computer figures out what are the best 10 numbers.
Yeah.
Is it possible to look at those how your model does that to figure out if there's interesting things? And
Yeah, I'm going to answer that in two ways. First, I want to say that when I'm showing you this classification model, I didn't tell you the full story, and we are, in fact, also allowing it to use hand-selected features like the peak magnitude, and those are super helpful in these classifications. Second, though, you can search for interesting correlations between those 10 neural network numbers and physical parameters that we are interested in. I haven't fully explored this, but there are no obvious linear correlations, so it's clearly learning something nonlinear about these light curves, if that's helpful. Yeah. Yeah. Yeah, so that's a really good question. Part of it is just, like I said, we have a very small sample of 1BCs. I think it's like 20 were actually photometrically identified, or I'm sorry, spectroscopically identified. But the second issue is actually like interesting, and I wasn't expecting it. So type 2s, when, do I have a plot? If you were to say type 2 to me as a time domain astronomer, I would imagine something like this on the other side, where it has this kind of plateau. So a 2P is what it's called. But actually, type 2s have a fair amount of diversity in them, and there's also specifically a kind called 2L, which just declines slightly faster. It turns out that the 2L, even to my eye, look a lot like, I'm not showing anything, but look a lot like 1BC. So that's really where this confusion is coming from, and with my own eye, I can see why that's happening. We've been trying to break this degeneracy using exactly what Paul is suggesting, features that aren't in this neural net, but it's challenging. Yeah.
Great, thank you.
Yeah.
Okay, thank you. So hi, I'm Grant. I'm from Warwick in the UK, and that's, what should I do? So what I'm going to talk to you about is a bit of a my favourite object talk. And the my favourite object is HT98-800 BABB. So it's a quadruple system is what I'm saying, and it's hierarchical in that there are two stars and two stars that are going around each other. And this is interesting. So this is a young star with a protoplanetary disk around it. So we're talking about 10 million years. And one of the reasons that this is a potentially interesting system to think about is that we know what the orbits of the binaries are. So if we have problems with protoplanetary disks, we don't understand, for example, what the viscosity in these disks is. So one way that we might be able to do that is if we know what the perturbation from a binary on the disk is, and we know what the disk looks like, then maybe we can learn something about the viscosity. And this is just showing a couple of SPH simulations of the inner part of a disk looking down from the top. Here there's a binary that's going around the plane of the disk, and here it's out of the plane of the disk, and the inner edge is different because of the interaction with the binary. So that's just sort of a proof of concept. So this is the system, and a sort of a summary of what we know about it. We know the orbit of the BA-BB pair quite well. So we have some astrometry, we have some RV, a double-line spectroscopic binary. We have an SED, which shows so the star is the grey line, and then this is the disk. So it has a huge infrared excess, which peaks at around a few tens of microns, suggesting that the dust that we're detecting there is moderately warm. And this is a picture of the orbital layout of the system. Back in 2010, Sean Andrews imaged this with the SMA and concluded that the disk was coplanar with the binary. It turns out that this was maybe a bit more marginally resolved than they thought. And this is the orbit of the A with respect to B. So then we applied for some ALMA time, and eventually we got it, and we got this fantastic image. The system is so bright, so that the signal to noise is kind of embarrassing. It's amazing. But I guess the important thing is that, so it's nicely resolved, it's a ring of dust, and the scale bar up there tells you that this thing is about the size of the asteroid belt. I guess what I didn't say is that these two binaries have about 1 AU semi-major axes, and the semi-major axis of the outer orbit is I think about 50 AU. And so what we get from this is we can see that the orientation of the B binary on the sky is something like this, but that is not the orientation of the disk. And what we get is that the disk orientation is either something like this or like this. We can't tell the difference. And so the question is which of those configurations is likely to be the true one? And the answer, which I'll get to in a minute, is that one of those is perfectly polar, or consistent with being polar, so the binary plane is like this, and the disk plane is 90 degrees, and the other one is somewhere in the middle. But we can do something to try and make an educated guess as to which we think is correct. The other thing that is less important for this talk, but so in the past it wasn't really clear if this was a protoplanetary disk, so a disk with about 100 times more gas than there is dust, that is in the process perhaps of forming planetesimals and planets, or whether it was a debris disk, so something like our asteroid belt, which is relatively gas poor. We've detected enough CO that it's consistent with being optically thick, which suggests that it's a protoplanetary disk. And the other thing is, so this is a velocity map, so the red stuff is coming towards us and the blue stuff is going away, and the extent is larger than the extent of the dust, which is something that we commonly see in protoplanetary disks. So this is a sign of inwards radial drift of dust in the disk. So why polar? It's not obvious, I don't think, why that would be a stable configuration. And so this is going to be a little movie which shows the orbit, the whole orbit of a test particle around a binary with an eccentricity of 0.77 whose pericenter direction is into the screen. And what you're going to see is that these are going to precess due to the non-1/r potential of the binary. So this is secular perturbations is the jargon. And what you'll see is the polar one, which is here, is going to stay still, and the coplanar one is going to stay still, and everything else is going to precess around. So the second from top left is what you would expect for something that's close to the plane of the binary, and it precesses around like drop a coin on a table or a hula hoop on the ground. And then if you're a little bit away from polar, then you get the same thing, but now you're doing it with respect to this polar orbit, so these are precessing as well. So we can show that in a slightly more nerdy dynamics way in this plot. So this is the inclination node phase space, and so all this so this is I cos node of the angle, I sine nodal angle. So if you're at the middle, then your inclination with respect to the binary is 0, and if you're here or up there, then you're polar. And if you put down a test particle around the binary somewhere on one of these curves, then you'll follow that curve. So if you're in here, then you're precessing in the plane of the binary, and if you're out here, you're precessing with respect to this polar configuration. Now that's for test particles. So if you do this with something that can that is dissipative, so a protoplanetary disk where there is shear and there is energy going into heat from that, then this is the same plot, but what you'll do is you'll spiral down to one of these two polar or aligned configurations. So this is showing it in terms of the time evolution, in terms of inclination and node, and this is showing it in this phase space. So you start out and you spiral down. So this suggests that you're going to end up in one of a coplanar or a polar configuration, and from what we've observed, we have something which is somewhere in the middle or a polar configuration. And so one thing that I did for this paper was a relatively simple SPH simulation starting out with those two configurations. And so I'll run this movie and you'll see that one of them stays basically where it is and the other one turns into a bit of a train wreck because it's trying to reorient the disk. And also the binary, it sort of tore up the disk because they're not particularly realistic initial conditions for a start. And what I think I've got time. What you'll find is that the misaligned one actually, over time, evolves to the polar configuration, and that's because the more eccentric the binary, the larger the phase space for these polar configurations. All right, I think that's enough. Okay, so what? I wasn't actually expecting to find the system to look like this. My proposal images look nothing like this, but it turned out to be interesting. So one thing that we can do, and this is sort of the opposite thing that I was thinking of, but this discovery precipitated a paper which was saying, okay, so what say we don't really know between whether we're misaligned or polar. We could use the size of the inner edge of the disk to diagnose which configuration we're in. And these are some surface density profiles for several different configurations. showing that the polar case has the smallest inner edge, and that's consistent with what we observe. And so that was their conclusion, is basically just sort of backing up our conclusion that it's unlikely that you would be misaligned. Now this turns out to be really cool. So in 2026, the A binary is going to go behind the disk. And so if we can monitor this in a sensible way, we will learn something. Presumably this is optically thick, so we're not going to probe the entire optical depth structure, but we'll get an idea of what at least the inner and outer edges of the disk look like, and we can do some spectroscopy maybe and see compare gas and dust extent. So this is just, each of these points was 1 year apart, so this was like 26, 7, 8, 9. So this is going to happen over about 4 years. And this is a high-res SPH simulation showing just the sort of thing, roughly in gas, that we might expect to see. Some spiral arms on the outer edge of the disk that are imposed by the outer binary. One last neat thing. So this polar configuration is only polar if the disk angular momentum is a lot less than that of the binary. So that's over here in this plot. But if the disk has a significant amount of inclination, then you don't exactly go to polar. And so I don't think you're only going to get an upper limit on the disk mass in this case. But in principle, this is a way to get a dynamical mass for a protoplanetary disk, which is important to protoplanetary disk people because they are having problems measuring masses because it's hard to detect hydrogen. All right, so that's in summary, this is a system where we know the binary orbits. That's the important bit, and we have a nice image of a disk, and hopefully we can learn about these protoplanetary disks. That's all. Thanks. So in this case, if you make any planets, they don't survive. So we did some in-body simulations, and you put down dust particles at a range of semi-major axes, and if there's no gas, then they get ejected in sort of million-year timescales. And so this is one of the reasons we conclude protoplanetary disks. So there must be something that's stabilizing the gas against these perturbations. So. But if you can make a system that is polar, quite likely this is polar because of this outer binary, right? So if you can contrive it in a way that you both make a polar configuration and don't have the thing that made you polar ruin your planetary system afterwards, then it can be stable. And they will just sit there in these 90-degree orbits. No, but I don't think we can't rule them out because the way that people find the circumbinary planets is look for transits in eclipsing binaries, and so instead, if you have the planet coming down like this from your EB, it's very hard to see. So I'm not saying that they're everywhere, but if they were, we wouldn't have been that sensitive. Yeah. So I expect that there's been some interesting dynamical evolution in the past of this system. So the typical way I would expect is you have some kind of fragmenting cloud core, and if it's a single star, you end up with a star in the middle and a disk around it. Maybe you can fragment that disk to make a binary, but then maybe you have other systems that are coming in, and maybe the A binary was captured. So I think that the way that I picture this is just sort of a standard disk formation, but with additional parameters because you've got extra bodies. Thank you. Oh, shit.
Okay, I am going to talk to you about stellar rotation with TESS. And let me just start by saying that rotation periods of stars are really important for many reasons. Earlier this morning I talked about why they're important for measuring stellar ages, but they're important for all sorts of reasons, not just stellar astrophysics or ages. They're also important particularly if you're interested in exoplanets. Rotation periods are really important because if you find an exoplanet transiting a host star and you want to go and do radial velocity follow-up of the system, you need to know the rotation period of the host star to make sure that you're not accidentally just detecting the stellar rotation period instead of a planet. So it's really important for lots of reasons, and we really care about making TESS into as optimal a stellar rotation mission as it can be. So TESS is an all-sky survey. It's going to measure very precise brightness variations of stars over the whole sky. And those brightness variations will allow us to detect transiting exoplanets and will also, in some cases, allow us to measure the rotation periods of stars, because stars often have dark spots on the surface which rotate in and out of view, causing some periodic variability in the light curve. And you can measure the rotation periods of stars from this periodic variability. But there's one feature of TESS data that make it kind of non-trivial for measuring stellar rotation periods, which is that some of the stars will be observed in the continuous viewing zone and will have year-long light curves, but most stars will be observed for just 27 days. And so this is kind of a problem because most stars, so if you have 27 days of data, it's very difficult to measure rotation periods that are longer than 10 to 14 days. And most stars rotate more slowly than that. Especially M dwarfs, especially cool stars. And the cool stars are arguably the most interesting ones for TESS because TESS is specifically searching for planets around cool stars. So we have to figure out how to measure long rotation periods from these short light curves. Spoiler, we're going to use machine learning methods. But before I talk about machine learning, let me talk about sort of how we'll build a training set for our machine learning algorithms. Fortunately, TESS is going to give us a perfect training set. It's going to give us all these stars observed with exactly the same instrument continually. And so if we can measure the rotation periods of stars in the continuous viewing zones using traditional direct methods, then we can train machine learning algorithms to measure rotation periods in the single sectors. So, to start with, we're measuring rotation periods for stars in the continuous viewing zones. And this is some work that's being done by a Helen Fellow at the museum. She's working with me for just a year. She's a post-bac. So the museum has this great fellowship for students between undergrad and grad school, and that's what Danielle is doing. She's currently applying for grad schools. So she's working with me to directly measure rotation periods to build a training set. And she's using various methods. There are many methods we can use to extract periodic signals from time series. I could spend so much time talking about this. But let me just show you a couple of examples for methods that we use. So I'm going to show you autocorrelation functions because I made a nice graphic which demonstrate how they work. So with an autocorrelation function, you take a light curve, you make a copy, and you slide it along itself. You calculate the correlation at a range of lag times. And then to measure a rotation period, usually you do some peak detection in the autocorrelation function. There are many ways in which we could improve this method. We could do sensible things like have a set of stars where we really believe the rotation periods and tune all of the heuristic knobs in the autocorrelation function algorithm until we predict the same rotation periods. Typically, people don't do that. I don't think anyone's ever done that. So that's something that we might try and do. Okay. Another method that we could use is Gaussian processes. So this is something that I have also spent a lot of time thinking about. Gaussian processes allow you to measure rotation periods of stars more precisely than sign-fitting periodograms, more accurately rather, because they are non-parametric or semi-parametric models that you can use to very nicely fit the data. Stellar light curves don't often look like sinusoids, so fitting them with sinusoids won't give you a very accurate rotation period. If you're interested in using Gaussian processes to measure rotation periods or to model stellar variability, there are a lot of resources now available online, lots of options for various places to go and get started. The goal, the sort of science goal of this project, other than creating a training set, is to see if we can detect this gap in the rotation periods of stars that Kepler found. So this is a rotation period versus effective temperature for stars with rotation periods measured from Kepler. And you can see this gap here is pretty much a complete mystery. We really don't know what's causing it. We have some hints. Understanding if this gap changes as you look in different parts of the galaxy might help us understand what's causing it. So TESS is a different stellar population than Kepler, so that's one of the things we're going to try and do with these stars. Okay. So then, leading into the stars in the single sectors, once we have a nice training set, we can start to understand how to pull out rotation periods for these single sector stars. Now, the tricky thing is obviously, for many stars, we're just not going to be able to directly measure the rotation periods. What we want to use is short timescale variability in the light curve that predicts rotation periods. So we know, for example, that granulation or flicker shows up in the light curve, and this tells you about the surface gravity of the star. So we can use that kind of thing to predict rotation periods. Rotation periods scale very neatly with stellar parameters. So if you know the temperature of your star or the color, or maybe even the mass, that gives you information about rotation period. The velocities of stars in the Milky Way, that gives you information about rotation period, because velocities tend to increase with age, and age tells you about a rotation period. So there are lots of pieces of information that you can use to predict the rotation period. And here is a very preliminary set of results that are actually just kind of an example created by Lucy Liu, who's a Columbia grad student who's just started working with me like a week ago. And she's already produced some results. So this is the true rotation period from stars in the Macquillan data set, so Kepler, and predicted rotation period using data that is not the rotation period and actually very little information. She's using random forest to do this, and she's using features such as stellar temperature, stellar velocity, the amplitude of variation in the light curve. These things all tell us about rotation periods. Why is this useful? This is particularly useful for those M dwarfs that have exoplanets orbiting them. If you find an M dwarf with a planet in TESS, you definitely will want to know the rotation period, and this is probably the way that you'll be able to get at it, unless you're lucky and it's a rapidly rotating M dwarf. I'm nearly done, but this is just showing that flare statistics also predict rotation period properties. So we're going to combine everything we can, flare statistics and stellar properties, velocities, Gaia information. If you were in my talk earlier, you've seen this slide so many times already today. I just wanted to throw this up there because this is a piece of software that does stellar age measurements. And all of this kind of new suite of methods for measuring stellar rotation periods with TESS will eventually end up here, because this is kind of a central location for all algorithms that are related to measuring stellar ages. I'm just going to leave this video up while I take questions. This is a website that randomly serves you a TESS-like curve every time you click hit me. And these buttons down the bottom, they do fun things too. So I'll let you figure it out for yourselves. Okay.
Are you taking this off of the full-frame images or the 2-minute cadences?
Good question. So to begin with, for the stars in the continuous viewing zones, we're using 2-minute cadence. Eventual plan is to provide rotation periods for everything, 2-minute cadence and full-frame images. So we're using the pipeline detrended products. We're also using Eleanor. And eventually the goal is rotation periods for everything.
Is one of them easier than the other? Like, does cadence matter to what you're...
No, cadence doesn't really matter. The timescales for stellar rotation are long. The timescales for granulation are shorter, but still half an hour should give you some information about granulation. Yeah.
We've heard about in the first talk that you're on big data, so I was wondering like how much of a computational effort is to produce this data product you're showing us. How easy would it be if you learn something new to kind of redo the analysis?
Good question. So the direct rotation period measurements are, so everything here is relatively computationally cheap. The only thing that's expensive is Gaussian process rotation period measurements. And with new technology coming from Danforth and Mackey's new algorithm, Celerite, which speeds things up a lot, using PyMC3 as well, also gives you a huge performance boost. That's actually becoming very tractable. But the machine learning algorithms that we're using are all really fast. So it's actually not a huge computational burden. Yes, but we also have computational resources from Flatiron. So if we need many thousands of CPUs, we have them.
What do you want? Yeah. I keep it? Okay. Good afternoon and thanks for inviting me. So my presentation is a bit different from what I've heard. And from what you are certainly used to. I would just put it in perspective. So you are looking at a distant object. Your playing field is the universe, and you ask what is there. And I'm part of the people who ask, could we go there and could we live there? So, and with the what's happening in the exoplanet field, I think this question has taken a brand new dimension. And so one of the questions I ask is, if I try to put everything in evolutionary perspective, and my question is, in this perspective, what is the meaning of space travel? Is it just, I would say, a marginal event using systems that you can put in space in order to conduct experiments and to have some application like telecommunication satellite? Or is it much more, is it a new emergence in the evolution of life and intelligence in our part of the universe? So I have no answer to that, but I tend to think that yes, possibly it is a new emergence. And of course, we have been very framed by the Apollo project and its success, success that has been celebrated in the last few months with the 50th anniversary of the landing of Apollo 11. But if you want to impact the future of civilization with space activities, you have to undertake very large-scale project activities, what could be called macroengineering projects. The fact that Apollo was really a macroengineering project, but it was very limited in time and scope. And unfortunately, 50 years later, we are not very far. We have not made many progress from there. So I will say a few words about someone who lived here in the region of Boston. I don't know if Frank Davidson. Frank Davidson was a professor of macroengineering in MIT for 40 years, worked with Jay Forrester. And he was one of my friends, dear friend, and he was a lawyer. He was a lawyer trained in Harvard, and he was a hero because he was one of the guys who came to France to land on the Normandy beaches to liberate France. And after that, he was also instrumental in starting the Channel project. And so he was a very, so he has not invented a big project, but he did a lot of things to try to make people understand what was the meaning of macroengineering. And macroengineering, you could say, is really linked to the development of civilizations on this planet. Very big projects have been very, very important. You can see from not only economic or political, but also cultural side. And for instance, the Giza Pyramid or the Great Wall of China, or in terms of infrastructure, the Roman roads, of course. So the idea of Frank was to say that even if not everything big is beautiful, you need a part of big project in order to build infrastructure and to help the development of the people on this planet. I will quote someone else. The economic dimension of future space activities has been really well said by John Marburger. He was the scientific advisor of George W. Bush, and in 2006 he wrote something that was for me something that was quite significant. He said, as I see it, the question of human spaceflight boils down to whether we want to incorporate the solar system in our economic sphere or not. And I think this is a major question. And in fact, the basic principle is known for a very, very long time. I say more than close to 1 century. It was expressed by Konstantin Tsiolkovsky, one of the 3 big pioneers of space activities, when he wrote that almost all the energy of the sun is uselessly wasted as far as humanity is concerned, Earth receiving only 2 billionths of what the sun emits. What's so strange about the idea of utilizing this energy? What's so strange in the thought of penetrating the endless space surrounding our Earth? I think, and this is a basic principle of this macroengineering in space systems. That is, using energy in space and using material in space to develop activities out of the Earth. And in fact, I'm back again to this era. The biggest project in macroengineering was not created by a space agency. It was created by an engineer in a company here in Cambridge. It was Arthur DeLittle. The guy was Peter Glaser, and in '68 he made the cover of Science magazine with an article on solar power station. The concept is very simple. You collect solar energy in space, you convert it in microwave, you send the microwave to the Earth, and you have a source of electricity that could be very interesting to replace all the fossil fuels. And of course also nuclear energy. And someone else from also this era, William Brown at Raytheon, was instrumental in making the studies on the way to transmit the microwave, the energy as microwave. So this is a very big concept, and this is really, I would say, the emblematic space macro project. Why? Because you think of the biggest object built in space now, that's the International Space Station. It's 450 tons, and it costed $100 billion to build. And it cost a lot to operate. And the SPS, the idea of Peter Glaser, was studied by NASA, by the Department of Energy, in a common study. And the subject, the results were really, it was a very big study. And the result was that it was possible with very big systems, such as this reference design coming out of this study. The satellite simply would have been 50,000 tons in GEO. So with a cost that has no meaning, because the space transportation cost was and is still an insurmountable obstacle. So I should have said that I knew also William Brown, that was, you see here the rotating antenna to transmit the energy as microwave. So clearly there is a big gap, to many order of magnitude, between what we do and what was thought by Peter Glaser 50 years ago. And also another example, not out of a space agency again, it was the concept of space colony from Jerry O'Neill, and it happens that I knew very well Jerry O'Neill too. And it started very simply. Jerry O'Neill asked his students in Princeton to what would they do if they had to design a space colony. And they came out by using very simple technology. And they came out with they showed that it was possible to build huge habitat for, something that was using a civil engineering method. Oh, so I have to move. Okay. So Jerry O'Neill ideas were showed that if you do everything in space, it should be possible to build huge habitat, and that living in space is not possible only on the surface of planets or satellites, but also in space in huge habitat. And what happened also was the idea that after all, what would do people in this habitat? Answer, they could build solar power station using resource from asteroid or from the moon. So all this, I would say all this came in the 70s, 80s after Apollo, when NASA was desperately trying to do something. And but it changed again in the last 2 decades with the coming of a few guys, entrepreneurs like Elon Musk. And Elon Musk has a different vision. His vision is that Earth is fragile in the cosmic environment. And in some way he is inspired by Carl Sagan. Carl Sagan said that the dinosaurs disappeared because they had not invented space travel. And so this idea is to create a second place where you can have most of the human culture, in order that if something happened on Earth due to Earth event or cosmic event, you can keep the result of all our cultural evolution for thousands of years. And I think that that's metal for me. It makes a lot of sense. So he came out with a very large project, macroengineering project, in order to create this second place to keep Earth's human culture. But at the same time, Musk has really taken a revolution in space transportation, going from a very small rocket to what's fly today, Falcon 9 and Falcon Heavy. And this huge project, the Starship, which is much bigger than the Saturn V of Apollo, and his goal is to really revolutionize the way you go in space and come back from space, changing it by orders of magnitude. So, in fact, it was the idea of NASA in the 70s. They were not able to do it, but the Starship would be totally reusable. But so the number put forward are really impressive. I don't know if he will succeed, but if he succeeds, it will change everything. Because at the moment, if you want to put 150 tons in LEO, it costs you at least $500 billion. With the Starship, it would be 10. So you are close to 2 orders of magnitude change there. Factor 50, maybe 100. And it changed everything because, and also, a Starship could take not only 2 or 3 or 4 people in space, but possibly 100. And also the same thing to the Moon, and same thing to Mars. So we could be at a critical moment where a new system, which is quite classical in terms of physics and engineering, could really make going and working in space much more easy and using resources in space really accessible. And this could be the beginning to jumpstart a cislunar and later solar system economy. And what Musk would like is to have a second second Earth in some way, but I'm not sure at all that it's a good idea to transform Mars, but with 1 million people living there. But it's not the fact that you have people living, it's that you keep the results of thousands of years of cultural evolution. And Jeff Bezos, everybody knows him, in fact, when he was a young student, he attended seminars by Jerry O'Neill, and myself, as I said, I knew very well Jerry O'Neill, and he was really fascinated by the idea. And now that he is the richest man in the world with a space company, Blue Origin, he would like to resurrect the idea of Jerry O'Neill. But frankly, I think that putting billions of people in space in habitat, I don't think it's a good idea. But myself, I won't like to live in such a big structure when you, in fact, you look at this image, to reproduce what we have on this planet. I don't think it's a good idea. So, and also if something like that happens, it will take centuries or more. So I don't think that even the richest man in the world could do it. So I'm much more interested by the idea to have to develop cislunar economy, solar system economy, using solar energy and extraterrestrial resources than by this project. So, and of course, one major macro project in space at the moment is Starshot. And this came back to my first remark. The question is, we don't want only to know what is there, we would like to know if we can go there. Thank you very much. First, Javier, my opinion on that, by 2050, I think the world will be barely recognizable. I think it will have changed so much. I'm interested by space, obviously, by also all development of all high tech. I think that the acceleration of all technological development at the moment, be it in materials, in biophysics, in everything, it's moving so fast that by 2050, the world will be totally different. And so I won't make, and it's not just, you cannot think of only a project like that as space is moving forward. Space will move forward. You will have also a lot of evolution in terms, for instance, of bioengineering. I don't think that the people who would live on Mars won't be different from us from a lot of point of view. And also, I think that lifespan will increase. So I think that we have the acceleration of what we could call progress, of at least of technology, acceleration of technological development is such that looking in 30 years, it's very, very, very far. And in space, at the moment, what is interesting me the most is that you have two scenarios. Or Musk succeeds with Starship, or he fails. If he succeeds, space will never be the same. It will open for your community, for instance, the possibility to put really huge telescopes on the far side of the moon, or to build in space incredibly large structure. Because simply, something that costs today 1 billion will cost 10 million. So it will be also, for instance, the Starship has a diameter of 9 meters. So that's very large. And also, you will learn in space to build systems using 3D printing technology. So you can really suddenly open new frontiers, and this extremely fast. What I've been very disappointed by what I think that has happened since Apollo. I think a space agency like NASA has not been able to really say what was possible using new technology. Musk tries, he may fail. If he succeeds, it will be totally, totally different in space. But, and it will also leverage what's happening in other domains, electric energy, I say bioengineering, and so on.
Thank you.